NASA just dropped a bombshell regarding the interstellar Comet 3I Atlas, and honestly, the entire astronomical community is still trying to pick its jaw up off the floor. We have been watching this object for weeks, documenting its flares, its rotation changes, and its erratic behavior, thinking we had a handle on its personality. We thought we had seen the extent of its tricks. But the new observations released today aren't just an update. They are a complete rewrite of the script. To put it bluntly, 3I Atlas doesn't even look like the same object anymore. If you were to place images from just a few days ago next to the data released today, you would swear you were looking at two completely different celestial bodies. This isn't a subtle shift in brightness or a minor orbital wobble. This is a fundamental physical transformation happening right before our eyes. To understand why everyone is so confused, we have to look at the sheer scale of the data involved. So this wasn't just one lucky snapshot taken by a backyard astronomer. This was a coordinated, multi-wavelength observing campaign involving visible light images, infrared data, polarization maps, and spectroscopic breakdowns. And essentially we threw every tool in the toolbox at this thing simultaneously. When the team started processing that data and lining it up against what we saw last week, the reaction was universal disbelief. The question wasn't, what did we find? It was, where did our comet go? Because the thing sitting in the crosshairs today bears almost no resemblance to the thing we were tracking yesterday. Let's start with the most obvious change, the one that you don't need a PhD to appreciate, the shape. A week ago, 3I Atlas had that classic picturesque comet appearance. It was a teardrop, a bright, rounded central region hiding the nucleus, surrounded by a soft glowing cloud, or coma, with a tail peeling away smoothly in one direction. It looked like a lantern moving through the dark, soft, and coherent. That is what comets are supposed to look like. But in today's high contrast images, that lantern is gone. The inner coma has lost its teardrop shape entirely. It has stretched out. The bright core region, instead of being round or slightly oval, is now elongated along a single axis, looking almost like a tiny glowing bar of light hiding inside the fuzz. It looks like someone grabbed the comet by both ends and pulled. Even more striking is the tail. Instead of flowing smoothly from this new stretched out core, the tail seems to have split. It now forms a shallow V shape, a forked path instead of a single stream. The visual comparison is jarring. We went from a soft rounded object to something that looks like a glowing spearhead, a sharp, elongated, and aggressive. In the slow-moving world of astronomy, comets simply do not change their fundamental geometry in a matter of days. It defies the standard timelines we are used to, suggesting a level of violence and activity in the nucleus is hard to model. But the visual shape is just the tip of the iceberg. When scientists switched filters to look at the data in different wavelengths, the mystery deepened in visible light. The comet previously held a steady greenish-white hue, the standard signature of fluorescing gas and reflecting dust. It was predictable. Now, that color profile has shattered. The stretched inner core appears whiter, harsher, and more stark, while the outer halo, the diffuse cloud surrounding the object, has taken on a distinct reddish tint. When you flip over to infrared data, which essentially acts as a heat map, the pattern flips. The outer coma is showing up significantly hotter and brighter than it should be, while the inner region isn't dominating the heat signal the way it used to. This isn't just a trick of the light or a change in viewing angle. When the light reflects differently, it means the material reflecting it has changed. The actual physical substance surrounding the nucleus, the mix of dust, ice, and gas has fundamentally altered its composition. So we are seeing this confirmed in the polarization maps, which is perhaps the most scientifically fascinating part of the update. Polarization measures how light waves are aligned after bouncing off particles, which tells us about the size, shape, and fluffiness of the dust grains. Standard comets have a predictable polarization pattern, strong at the edges, weak in the center. 3I Atlas has broken that rule completely. Today's data shows a band of unusually high polarization cutting across one side of the coma like a stripe, while the opposite side shows readings far below model predictions. In practical terms, this means the comet is no longer shedding material uniformly. One side of the object is spewing out a completely different type of dust than the other, perhaps large, compact chunks are flying off one face, while fine fluffy powder is blasting from the other. We are looking at an object that is shedding different skins from different parts of its body. It creates a picture of a nucleus that is complex and heterogeneous, not a uniform ball of ice, but a patchwork of different materials that are reacting differently to the solar fire. The timing of this transformation is the piece that ties the narrative together, working backward from the speed of the jets and the expansion of the new tail. Scientists have realized this didn't happen over weeks. It happened in days. Somewhere between the last observation window and this one, a switch flipped. The leading theory is that we have burned through the outer layers of the comet and hit something new. Imagine the comet as a geological jawbreaker. For months, it has been shedding relatively similar outer layers, producing consistent activity, but now we have stripped all of that away and hit a deeper, ancient stratum material that has been locked away in the dark since the comet formed around a different star billions of years ago. This new layer clearly has different properties. It reflects light differently, creating the color shifts. It breaks apart into different sizes of dust, causing the polarization anomalies. And it is erupting from new or widened vents, causing the shape to stretch and the tail to split. We are literally watching a new chapter of this object's history being excavated in real time. We are seeing the fossil record of an alien solar system being vaporized and displayed for us on a cosmic screen. Interestingly, despite this visual chaos, the orbital dynamics team found that the net thrust, the non-gravitational push caused by the jets, hasn't rotated much. This implies that while the type of material coming out has changed, the location of the vents hasn't T-migrated across the surface. The active regions are likely in the same spots, but they are evolving. Cracks are widening, deeper reservoirs are being tapped, and the pressure is ramping up. The engine is the same, but the fuel has changed. This brings us to the uncomfortable question of what happens next when you strip away the outer shell of a structure, expose the volatile interior, you risk structural integrity. The more layers we peel back, the more the physical properties of the nucleus shift. Its mass distribution changes, its rotation torques change, and its internal stresses ramp up. If the outer shell was a protective crust and the interior is looser or more volatile, what we are seeing today might be the prelude to a catastrophe. We are essentially looking at two scenarios. In the first, the comet finds a new equilibrium. It smooths out into this new elongated configuration, maintains the double tail, and rides out the rest of its solar encounter as a weird but intact object. In the second scenario, the structural changes become too much, and the asymmetric jetting creates a torque that tears the weakened nucleus apart. We might wake up next week to find that the bar shape has resolved into 2 or 3 distinct fragments drifting apart. NASA is careful not to use the word breakup just yet, but the drastic change in appearance is a classic symptom of a nucleus under extreme stress. We have never seen an interstellar comet do this. Oumuamua was a ghost passing through before we could really look at it. Borisov was a model citizen acting exactly like a normal comet. 3I Atlas is in a league of its own. It is wild, dynamic, and unpredictable. It is teaching us that interstellar objects can be far more volatile than we imagined. The fact that these changes are happening on human timescales, days and hours, not centuries, makes this an unprecedented observational opportunity. The next few weeks are going to be critical. Every telescope capable of pointing at 3I Atlas will be tracking it, scrutinizing every pixel for signs of fragmentation. We are tracking a transformation that feels increasingly like a cliffhanger. We are not just watching a rock pass through our neighborhood. We are watching a visitor from another star system undergo a violent metamorphosis. Whether it survives the process or crumbles into dust, we are witnessing a rare and spectacular event. In the history of astronomy, we might not see another object like this for decades. So whatever 3I Atlas does next, the entire world will be watching.